So let's start. So I want to begin from the very elementary notions. So first of all, the base field. Is the field of complex numbers. And my notation usually will be as follows. G or H will denote some finite groups. Finite group. And representations will be denoted as representations will be denoted by capital T or say U or V. And the space of representation will be denoted as H, maybe H of T. So the first definition, what is a representation? I will assume that the groups are finite and all vector spaces are finite dimensional. So the first definition is what is a what is a representation? Representation a group G in a vector space H is a homomorphism from G to the group of invertible linear operator on the space H. So I will denote a representation, say, by T, or sometimes I will write T H. So these are two possible ways of notations. So the first example, why in principle representations do exist. So the first example is the so-called permutation representations. So we assume that we are given some G space X, which means that it is a space, say, finite set, endowed with an action by G. The action may be is left or right. So left action, the map satisfying usual axioms, so right action. So assume we are given such G space, and take the space. This is the space of functions, complex valued functions on X. And then we have a representation. This produces a representation of the space functions, which are defined as follows, depending on the kind of action. For the left action, the formula is as follows. So assume G is a group elements, then the corresponding operator, this is the operator on our space H, which is the space of functions. So the formula is as follows: being applied to a function f and then evaluated at a point small x, it is defined as follows: G inverse x. So in order to have a left action by G here, you need to invert and have essentially the right action. This is the usual rule. Or in the case of a right action, the formula is as follows: sometimes it's convenient to deal with right action, which depends. Here, this is the point of our set, and G and F and some questions. Yeah. Okay. Now, given the representation, we want to construct new representations. So there are several ways to build new representations starting from initial ones. So one way is as follows: given representations, U1, operating on the space one. I'm sorry, switch off the microphone, please. We can produce the direct sum, which acts on the direct sum of the spaces in a natural way. So this gives us the direct sum of two representations. And likewise, we can produce tensor product acting on the tensor product of our spaces. So for instance, once we're given a single representation from a single representation, we can already produce a whole family of representations, like by taking, say, tensor powers, which acts on tensor powers of our spaces. Here M, 1, 2, 3. So is it clear? I hope. Do you have any questions? Is it okay? Well, what next? But why representations exist? The simplest way to see this is to use the so-called regular representation. Regular representation of G. I recall G is a finite group. So the group itself already carries a natural representation. Namely, we take the space of functions on G, and G itself is a G space. G is a G space because we have the multiplication map. So we get a left action if you view this copy as X, or we have a right action if we regard this copy as X and this one as X, so we get a right action. So from this we can produce a representation following this scheme, this general scheme, and it's called left or right regular representation. The next definition I need is that of unitary representation. Unitary representation. So I assume that H, our space, is a finite dimensional Hilbert space. Finite dimensional Hilbert space. Which simply means that H has a scalar product. Scalar product. As usual, the scalar product here is assumed to be non-degenerate, linear with respect to the first argument, and antilinear with respect to the second argument, as satisfying the property of Hermite scalar product. And of course, it also should be positive, meaning that psi and non-degenerate means that happens only if psi is equal to 0. So this is pure linear algebra. So assuming this, we consider the group U of H, the group of unitary operators on our space, and then a unitary representation is a morphism of G into this unitary group. So this is the definition of unitary representation. So we simply replace the group of all invertible operators by its subgroup of unitary operators, smaller. The next notion I need is equivalence. Equivalence. What is this? Quite a natural definition. If you have two representations, T1 on H1 and T2 on H2, we say that they are equivalent and write this as T1 tilde T2 if there exists a linear isomorphism between the spaces such that it transforms one representation to another one, which means that we have a commutative diagram. So this is isomorphism, linear. And the same. And for any G, small g, in our group, we have an operator, T1 of G and T2 of G. And the condition is that this diagram must be commutative. So this is, I believe it's quite clear. But in case of unitary representations. One usually assumes that the structure which is necessary is preserved. One assumed that this map, this isomorphism, is isometric. It's isometric, meaning that it preserves a scalar product. Okay. So the first result, very important, simple but important, means the following theorem. Any representation T, I repeat, of finite dimension and of a finite group is equivalent to a unitary representation. So the idea is as follows. What we have to prove? We have to prove that there exists. We want to prove there exists a scalar product. Scalar product, which is G invariant. G invariant. Meaning that we have this equality, the scalar product, should be equal to this one for any psi and eta in our space and any element of our group. So we want to have such a scalar product. But how to construct it? The idea is as follows. Take any scalar product. Say, denote it. And we can average it. We can which means as the following. The new product is defined as follows. Take the transformation of the initial scalar product and take the sum of all elements of our group. And if we want to have averaging, one can, it's not necessary, but one can divide by the order of our group. And it's a little exercise, an observation that this new product is already G invariant, meaning that it satisfies this relation. And the rest satisfies, which in turn means that the representation is unitary with respect to this new scalar product. Why? But because if you insert here some element, and here also this one, this operator, what happens on the right-hand side? We have to insert H inside this, but this expression remains intact. So this is the idea of averaging. Is it clear? Some questions maybe? So please ask if something is not completely clear. So this is simple, but very important. So we can assume from now on that our representations are unitary. Sometimes I will drop this assumption. Sometimes I will assume that I am dealing with unitary representation, depending on the situation. Okay, so the next notion is that of irreducible representations. Irreducible representation. What means irreducibility? So if you have some representation, and assume that we have a subspace. Assume we have some subspace, say H prime, inside H, which is G invariant, meaning that our operators transform, but because they are invertible, this exactly means a condition of invariance with respect to any element of our group. In this situation, we say that this is an invariant subspace. So irreducible means no proper invariant subspace. Proper means that we want to exclude the zero space and the whole space. They are obviously invariant, but besides, we exclude any other invariant subspace. In this case, we say that our representation is irreducible. And the notation which one uses in this situation is as follows. G hat is the set of equivalence classes of irreducible representations. We will see that it is a finite set, but at present it's not clear from the very beginning. And the next claim is as follows. Proposition. Any representation T is completely reducible. What means completely reducible? The definition is as follows. Given some question? No? Given an invariant subspace, I will assume it's a proper invariant subspace. There exists an complementary subspace. Complementary subspace, which is also invariant. So we can, in this case, we can write our H as a direct sum of two subspaces, and we can restrict our representation T on this one and on this one and get a decomposition of T into direct sum of two representations. And some little remark we can assume T unitary. So we can assume that our space H has a scalar product. And then we can simply take the orthogonal complement. From the very definition of unitary representations, it follows that once our subspace is invariant, its orthogonal complement is also invariant. So this is proved. We obtain this claim, the existence of a complementary invariant subspace. And then the corollary is the following. So T, any T, can be decomposed into, one can say, orthogonal direct sum of irreducible representations. Sub-representations. So what is the meaning of this fact? It means that irreducible representations are building blocks. Any representation can be built from irreducible representations. So this is why one is often interested in constructing all irreducible representations. The next notion is that of intertwining operators. So assume we are given again two representations. The same group as usual. And the intertwining operator is a linear operator from one space to another space, which commutes with the action of G. So this is the same picture as above, only I don't assume that this is a linear isomorphism, arbitrary linear map making such a diagram commutative for any element of our group. So such an operator is called intertwining. One can write it as follows. So one can write it as follows. Commutation relations. Any mod G. This is very important for us. And I will denote by home in T1 and T2 a space of intertwining operators. One space to another. And this is a linear space. This is linear space. It's easy to see because if all linear operations, addition and multiplication by scalar, preserve the intertwining property. So this is some linear space. And well, now we come to the famous Schur lemma. Probably you know all that in the course of algebra, but nevertheless, I would like to repeat. So assume that we have two irreducible representations. This notation already means that they are irreducible. And we have two cases. One is that they are not equivalent. And then the space of intertwining operators is trivial, only zero. And assume the opposite, they are equivalent. Then this space has dimension 1. Or this can be rephrased as follows. So one can assume that T1 and T2 are just the same. Then this means that the space of self-intertwining operators is one dimension. But what this means? It is just the scalars. So how to prove this? This is very easy. Very easy. Just apply the very definition. But nevertheless, it's important. The base field is C, algebraically closed. So how to prove this? So assume that we have some. So the first claim, so assume. So if the first step, proof. First step is to see that once T1, T2 are irreducible, it follows that the kernel of A is either 0 or the whole space H1, because the kernel must be invariant subspace. So it is either 0, either the whole space. And the same for the image. Or maybe image is a bad, I'm sorry, range. Range is also either 0 or the whole space. And from this, it follows that there are no so the only possibility is that the only possibility is that A is bijective, but this is excluded because the representations are not equivalent. So here we don't need to use the assumption that the base field is algebraically closed. But in the second part, when we assume that T1 is equal to T and want to prove that any intertwining operator A is scalar. How to do this? The idea is as follows. We already have scalar operators which are intertwined. So take A minus lambda, where lambda is some complex number. And 1 is the identity operator. And we see that such an operator is also intertwining. Okay? So because the field is algebraically closed, there exists some lambda such that is an eigenvalue. But in this case, we get some invariant subspace. And this invariant subspace is always, should be trivial, either 0 or the whole space. And this means that actually, but this is excluded. And so we conclude A is simply equal to this scalar. Okay? Because otherwise we would obtain some non-trivial invariant subspace, the eigen subspace corresponding to lambda. So this is the Schur lemma. The next remark is the additivity property. For this space, the space of intertwining operators. I recall that this object is a vector space. I have a claim that one can say this is a functor, but I don't want to use this terminology. So I want to claim that this object is additive with respect to both arguments. Which means that we have a canonical identification. If our representation T1 is written as a direct sum, of two representations, then this induces a canonical decomposition such a kind. And if our representations are unitary, then the direct sum are orthogonal. So if representations are unitary and if this decomposition is orthogonal, then this one is also orthogonal. And like
Sorry, in that line, shouldn't be T2 tilde, not T1 two tildes.
sorry, I don't understand. Repeat, please. Oh, maybe.
В строчке предпоследней там у вас T1 с двумя черточками, вроде должна быть T2.
Да, спасибо. Это правильно. Thank you. And likewise, for the decomposition of T2. So this is very easy to see. The next definition is that of intertwining numbers. Intertwining number is denoted as a new between T1 and T2. This is by definition the dimension of the space of intertwining operators. Okay, so what next? So, right, let's take our space G hat. The set of all irreducible representations. Let's enumerate them. Actually, there are finitely many of them, but don't think about this at the moment. And assume we have two representations, T1 and T2. And I already proved that any representation can be decomposed on irreducible ones. So we can write T1 is a direct sum of irreducible representations. Some of them can be equivalent or some are not equivalent. Okay, not equivalent. So write this as follows. T1 is the direct sum of our irreducible representations. And this notation means that we have a direct sum of some number, sub I copies of this representation. So in my notation is T just means T plus T plus T m times. So we can write some m, formally some numbers, some can be 0. So this just means that we have dropped this component. And likewise, we can write and both sums are finite or because we don't know formally yet that this set is finite, we can only assume that in this decomposition there are only finitely many non-zero multiplicities. And the conclusion is as follows. The claim. The intertwining numbers between our representations is equal to this sum, which makes sense because only finitely many of these multiplicities are non-zero. So this is the claim. And what is the proof? Proof is very easy. So proof. You have some extreme cases. Extreme case. T1, T2 are irreducible. Then we have the intertwining number is either 0 if they are not equivalent, or 1 if they are equivalent. So this is the Schur lemma. So combine this with the additivity property. See? We get the claim. Get this claim. So is it okay? Is it clear? So the first corollary is the symmetry. This is the same as this quantity. The next corollary in the decomposition such a kind of decomposition where are irreducible and pairwise non-equivalent, the multiplicities are defined uniquely. So if you have any other decomposition, the multiplicity should be the same. So what is the proof? Very simple. We just remark that the given I, the corresponding multiplicity, is just equal to the dimension of the space of intertwining operators between these irreducible representations and our T. And so this quantity is defined canonically. So this one is also canonical. And this leads us to the following definition. Let's say that T is primary. Primary if it is equivalent to the direct sum with some irreducible T prime. So T should be, so the definition is that T can be represented as the direct sum of some number of copies of a certain irreducible representation. And the next claim, no, sorry, the definition. The primary decomposition is the decomposition of our representation T is the following. Where each Ti is primary and the corresponding irreducibles, say Ti primes, are distinct. Non-equivalent. So this is the definition. And we know that a primary decomposition always exists. But the claim now, take a primary decomposition. Also, these components are also called often isotypic components. Typical. Proposition is as follows. Assume that we have some T in a space H and take its primary decomposition, which means in particular that our space is the direct sum. And we may also assume that this decomposition is orthogonal if our representation is assumed to be unitary. This holds automatically. And the claim is this, as follows. Any invariant subspace, our space H, is compatible with H right? Is compatible with the decomposition. Dot star. What means compatible? Which means that meaning that our H prime is the direct sum of its intersections with these components. Why? So the proof goes as follows. Look at this decomposition. This decomposition of our space. So, for instance, we can write H A, and once we have such a decomposition, we can represent, maybe better to say, can write any operator A on our space H as a block matrix. A block matrix operator varied. Just means that A can be written in this form. Where what are these quantities, the entries of this formal matrix? Assume that Aij is an operator acting from the J component to the I component. So is it clear? One can say also, say the following, that Pi, assume that it's the projection from H to the component number I.
Excuse me, is A an operator that acts on H? It's just that on the...
Yes, thank you. This is stupid what I wrote. Thank you. I mean this. Thank you. So we can identify with This is not formally, it's not exactly the same, but these two objects can be identified more precisely. One can say that this one is the restriction of this operator on these components. Okay. So this is a formal definition. And because we have a decomposition of a unity, we can write the sum which is equivalent to this presentation. This is equivalent to this one, okay? But now, what we want to say now, we have that if I is not equal to j, then A is an intertwining operator this implies that this component must be zero. Why? Because otherwise we would obtain we would a non-trivial intertwining operator from two this is my notation from the irreducible representation which enters the component number j. But this is impossible. This is impossible by the Schur lemma. So this means that A is block diagonal. So we have proved that any intertwining operator is actually block diagonal. So the components outside the diagonal are zero. And from this we can already conclude that our invariant subspace is compatible. Why? A way to do this is assume that our representation is unitary, and this decomposition is orthogonal, and then we have for unitary operators, for unitary representations. There is a bijections. Have a bijection between invariant subspaces. And projection self-intertwining, maybe it's better to say self-intertwining operators. So that is self-intertwining operators, which are also projection operators. And because of this one-to-one correspondence, we can switch from invariant subspaces to projection operators, which are intertwining operators. So combining this remark with what I proved, we obtain that once any self-intertwining operator is block diagonal, this just means taken, if you take as a projection onto orthogonal projection onto an invariant subspace, we get this compatibility claim between it. Is it clear? Is it okay? And what next? The next claim is some corollary. So the primary decomposition, or in our words, decomposition into isotypical components is unique. So this is easy to see once we know how to obtain all invariant subspaces. It's a little exercise to see that we have this claim. But I would like to mention that this remark that decomposition into irreducible components is not unique. In what sense? Of course, the multiplicities are defined uniquely, but the varied decomposition is not unique, which is seen from the following observation. So take even a primary representation. T is prime m times with T prime irreducible. And what are now we can write in this situation, one can write our space H can be written as follows. We take the H prime, my H prime is the space of T prime, and take the tensor product with the m-dimensional vector space. We can write this. And now the claim, so the claim under this identification I would like to repeat with writing H as a direct sum. This is equivalent to writing it in this form. Okay. So this is convenient for us because from this presentation one can deduce under this identification in this one intertwining operators are precisely operators of the form which means that here X is some operators acting on this space and tensors with the identity operator. This is a little exercise to prove this. This is essentially a particular case, of this claim. No, not exactly. Okay, but anyway, I don't want to prove it just now. Try to do this. And now one can see that it follows that decompositions for primary representation E with T prime irreducible are in a sense governed by the group of invertible operators on this space. So once we have one decomposition, we can get from it another decomposition by applying an operator, an invertible operator on this space. So there is the source of non-uniqueness of a decomposition of a primary representations into irreducible. And maybe I have 5 minutes after all this a little bit boring claims to abstract, I believe simple but abstract, some more concrete examples. Some examples. So let's return to the permutation representations. So take X1, assume these are G spaces. So I recall these are finite sets with an action of our group. And take H1 is the space functions H2 space functions x2 and T1 and T2, the corresponding representations on these spaces, and how to compute the intertwining numbers. I recall that this is the dimension of the space. I'm sorry, I would like to write a little bit differently from T2 to T1. There is no difference, but it's a little bit more convenient. And we claim is as follows, that this quantity can be computed as follows. Take the direct product of our sets, and there is a diagonal action of our group G acts diagonally so this just means that for the left action, the action of some element G applied to a couple of points is this one. So the claim is this is the set of orbits. We take the diagonal action, the quotient space, that is the set of orbits, and its cardinality. So this is the claim. This is the claim. So the idea, we have 2 minutes to prove. The proof is as follows. There is one-to-one correspondence between operators A acting from H2 to H1 one-to-one correspondence and kernels which are simply functions in 2 variables. Functions on x1 cross x2. So this is easy to see that just we write our operator applied to a function f, evaluated at x1. It can be written as the sum over x2 our kernel. So this is easy. I think this is trivial, but now we see that the condition that A is an intertwining operator is equivalent to the relation by the very definition G, and this can be seen as
Excuse me, what is the space, the second space in the one-to-one correspondence? Could you repeat it, please?
I would like to say that any operator, this claim is independent of any mention of representations. Just means that if you have a space of functions on one set, I'm sorry, I want to say that sorry, I need to write. This is the function. I want to say that any operator acting from the space of functions on x2 to the space of functions on x1 can be represented in this way.
What does the K mean?
There is a one-to-one correspondence between the operators and this function in two variables. This just means that an operator can be represented by a matrix.
So that's just all the functions on the all the functions on x1 cross x2, right?
Yes, there is one-to-one correspondence between operators and arbitrary functions in two variables.
Thank you.
Is it clear, or maybe I can repeat? Or I can make it more explicit.
Yes, it's clear. Thank you.
Clear, okay. So the final step is just to remark that this condition just means that our kernel is G invariant. So this is just equivalent to G invariance of K, which means that K x1, G x2 should be equal to this one for any G. So this is a little exercise to prove this. And now we see that the dimension of the space of G invariant kernel is just equal to the cardinality of the orbits, of a set of orbits. Okay? So if we have representations which are realized as permutation representations, we can immediately see how to compute the intertwining number. Just look at the orbits of a diagonal action. I'm sorry, just one minute. So some corollary. Corollary is as follows. So assume that X1 is a homogeneous space or some subgroup. And this is also homogeneous space with respect to probably another subgroups. Then we have this can identify this set with the space of double classes. Little exercise again, and then applying this claim, one can see that the number the intertwining number between two representations, two permutation representations related to this picture, the homogeneous spaces, is equal to the number of double classes with respect to these two subgroups. So let me stop at this moment. I'm sorry to be late. 5 minutes. So let me switch off recording.